Okay, we'll get started. Looks like the rest of the class is enjoying the break while. Okay, so today I want to talk about observability and constructibility. I want to start with a motivating example. So let's assume that we all work for the facilities manager at Ohio State University. We have a whole bunch of buildings and we have storm drains. So storm drains would look something like this. Okay, so this is the storm drain and it's collecting rainwater from the catchment area, and then we have the levels of water. So this is my x2, this is my x1. So these are the two states that I have, and then I'm observing the total flow of water from here. So this is my Olentangy river. And so the water is flowing into the Olentangy river. So the storm drains are collecting water from all the buildings across OSU and sending the water, routing that water to Olentangy River. And the university has given you $20 to buy a sensor and put it on this draining system, storm drain system, so as to make sure that we don't have overflowing storm drains, right? So whenever you have overflowing storm drains, what happens? You have like a water puddle all over the area, and that's not a good thing to have. Now here is my question to you. If there is no water flowing from this drain, what can you say about x1 and x2? They are zero, right? So there's no water flowing from this drain. X1 and x2 is zero. What about there is some amount of water? Let's do not assume that these are saturated. So assume that there's still some capacity left for the water to flow out of this pipe. So it's maybe half of its. So the flow out of this is half of its capacity. What can you say about x1 and x2? So this is your y. This is what you're observing. You just put one sensor here. You haven't put the sensor there because the university wants to cheap out on sensors. They just want to give you $20 of budget. And in $20, only one sensor can be put here, which measures what the total flow of water out of this pipe is to the Olentangy River. Okay, so all I can measure is y. I don't have enough budget to measure x1 and x2, but my question is, by looking at y, can I infer x1 and x2? If y equals to 0, x1 and x2 is equal to 0. If y is non-zero, can you say something about x1 and x2? What do you think?
And shouldn't we also consider the radius of these drains?
I mean, yeah, I don't want to have a very, very sophisticated model for this draining system. Generally speaking, the outflow from each drain is a function of the x1, but not necessarily of the radius, because the pressure is a function of the height of the fluid, not of the radius. Does that make sense? The volume doesn't matter, it's the height that matters, that influences the pressure, and that pressure is what sends the water flowing through the pipe. Are you a mechanical student or electrical student? Okay.
But I'm not mechanical.
You're not mechanical? Okay, then you are excused from answering this question. Right. So people in chemical engineering and people in mechanical engineering, they worry about this a lot. People in electrical worry about this. Okay, now here is your question. I have a battery or maybe a cell. I have connected it in parallel and I'm measuring the voltage. I'm measuring the voltage of this. By knowing the voltage here, can you tell me what the current going through this cell is and the current going through this cell is? Okay, so that's An equivalent question. Do you know the answer to this question?
So if the circuit is open, there is no current flow. But if you are saying like there's some internal resistance of the battery, then
Yeah.
there might be some current.
Right. So assume this is a 10-year-old car, and all of these cells were put at the beginning of whenever that car was manufactured. So at that time, it was the same cell, but over time they have aged differently for whatever reason. One cell was outside, so it was exposed to the environmental condition. One cell was inside, so it wasn't exposed to the environmental condition. Okay, so it's the same idea. I'm measuring one thing, but I have a whole bunch. You can think of it as like in an actual car battery, you have cells connected in parallel, like hundreds of cells connected in parallel. And all you are measuring is the voltage across this cell pack. Okay, so we want to study this problem today, which is I'm measuring something. I have a sensor. I'm measuring something, but my state actually is much larger than what I'm measuring. So I'm measuring a small percentage of my entire state space. And the question really is, can I infer information about the entire state if I only have an output measurement or measurement from some bunch of sensors. So that's studied under the umbrella of observability and constructibility. So let's look at the definition. Okay. So we are looking at a linear system. We have a linear observation equation as well. This is something that we have talked about many times. What is the expression for yt given x naught and the entire sequence of ut that you have Let me put x0 equals to x0. Okay. So this is what my observation looks like as a function of time. Let's say my problem is my t naught is equal to 0. So what observability means, that if you give me the information after t naught, I should be able to reconstruct x t naught. Constructibility means give me the information prior to t naught, and I want to be able to reconstruct what x of t naught looks like. So maybe given the instantaneous observation, I cannot figure out what the state is, but if you give me the history of observations, the history of control, probably I should be able to figure out what the state is. Okay, so constructibility is giving you the history prior to t naught. This one is giving you the history after t naught. Okay, and I want to be able to reconstruct x t naught. So I'm going to solve a simpler problem because these are time invariant systems. So I can just look at, I just want to reconstruct x naught. Okay, given my observation, and so far, like for the first half, let's just focus on observability. We'll talk about constructibility maybe towards the end of the class. So for now, my goal is you give me yt and ut, t greater than equal to t naught. I want to be able to reconstruct x of t naught. And yt is given by this expression. Now ut is also given to me, right? Ut is also part of my information set. So in fact, I can compute this integral and I can compute this value. Sorry, d is not a function of t. So this is just dot. D is not a function of t. So this is the part that depends on so what I'm going to do is construct y tilde t equals to yt minus this whole thing here, which is c f at x naught. Now y tilde t is independent of the history of ut. So given yt and given the entire history of ut, I have constructed another variable y tilde t, which is actually independent of ut. So in fact, I have removed ut also from this consideration now. Okay, so what does observability mean? That if I set my ut, so sorry, when is a state unobservable? When can I not? When will I, even if I look at y tilde t for the entire duration, I won't be able to deduce what x naught is. When will that happen? So that's the definition of unobservability. Definition 5.34. X is unobservable if and only if ut is identically 0 for all t, implies c e raised to at x equals to 0 for all t greater than equal to 0. And then we say AC is observable if and only if RO bar is 0. This is called unobservable subspace. Okay. So the goal for today's discussion is to characterize the subspace of unobservable states and to identify under what conditions is AC observable. So if my matrix A is right here, matrix C is right here, what should be the property of A and C so that the set of unobservable states is only 0. Okay, remember 0 will always satisfy this condition, so 0 is always part of the unobservable subspace. But the question is there non-trivial unobservable subspace for a specific system? The reason why it's a subspace is if X satisfies this condition, then if you scale X, multiply X by alpha, that would also satisfy this condition. And if X1 and X2 satisfies this condition, you add the two X1 plus X2, that will also satisfy this condition. So that's why it's a subspace. It's not just a regular set. It looks like a plane in Rn. So this would be unobservable subspace. It would be a hyperplane in Rn, or it could be a line in Rn, something like that. Okay. Any questions so far? Yes, please.
So I guess if, I'm not sure if you mentioned this earlier, but if B and D are zero vectors or zero matrices,
right,
does that automatically make it a X observable?
Not quite, because you see what the B and D matrix appears here in the expression for Yt, and I'm going to subtract this from Yt in order to get Y tilde T. So now my expression is only a function of A and C. B and D doesn't participate in that. Now, of course, situation would be quite different if you didn't know your B and D matrices, which kind of happens in reinforcement learning situation, but we're not talking about reinforcement learning here. Any other question? Okay. Just like controllability or reachability Gramian, we have observability Gramian. This is represented by WO0T, which is equal to integral 0 to T exponential of A transpose tau C transpose C exponential of A tau d tau. This is in Rn cross n. and we have observability matrix. I'm going to denote it by script O, which I'm going to denote like this to differentiate it with 0. This is given by C, CA, CA raised to n minus 1, RP n cross n. P is the dimension of Y. So U is m dimensional and Y is observation is P dimensional. I have P sensors in my system. So these are all the definitions that we need to keep in mind for what's going to come next. Okay, so once again, what the train of thought is, I have a linear system. I can compute yt as a function of x naught and the entire sequence of ut that I've applied. Turns out that because it's a linear system, I can isolate the effect of the control actions. I can subtract it from yt. I get y tilde t, which is purely a function of c and a and x naught. And my problem is, by looking at y tilde t, I want to be able to figure out what x naught is, right? So by looking at this whole sequence of observations, updated observations, so I've deducted all the observation that I'm seeing due to the control. So I've deducted that. So I'm looking at this observation, and by looking at this observation, I want to be able to deduce what the value of x naught is. Okay, I'm looking at observability only. So I'm looking at t greater than equal to 0. So I define this notion of unobservable x. So state x is unobservable. If I input 0 control and I look at the output is uniformly 0 for all time t greater than equal to 0. Okay, the set of unobservable states is denoted by R0 bar. So O here refers to observable, bar here refers to unobservable, right? So this is this is observable. This is the unobservable subspace, and we define AC to be an observable system if the unobservable subspace contains only the 0 vector, no other vector. In order to understand the observability of a system, I need to introduce these two notations, observability Gramian and observability matrix. Okay, so these are the two things we need to keep in mind, just like we did it for reachability, no different. As we did in the previous lecture, from Cayley-Hamilton theorem, let me write it here. Right, so this follows from the Cayley-Hamilton theorem. We talked about it in the previous lecture and the lecture before that, just using that expression here. And now I have a bunch of results, and we'll spend the rest of the class proving those results. So lemma 5.36, which says that the null space of the observability matrix is the same as the null space of the observability Gramian. For all t greater than 0. And then we have theorem 5.37, which says that the unobservable subspace is the same as the null space of observability matrix. And then we have corollary 5.38, if NO is 0, O is full rank. Then X naught can be given by okay. What are these results? Remember, in the reachability case, we had talked about the reachability of, the range space of the controllability matrix is the same as the range space of the reachability Gramian. Here, the situation is slightly different. We are talking about the null space, no longer the range space, but the null space of the observability matrix is the same as the null space of the observability Gramian for all t greater than equal to 0. I guess equal to doesn't matter. It has to be greater than 0. Then the second theorem says that actually the unobservable subspace is the same as the null space of the observability matrix. And by this particular equivalence, it's the same as the null space of the observability Gramian. So we have characterized what the null space is going to look like just by knowing what the matrix C and A looks like. And then the third result that I want to talk about is if observability matrix is full rank, then in that case, this particular matrix is invertible because this is also full rank and this is a square matrix and it's a full rank matrix, as a result of which this is an invertible matrix. And if it is invertible, I can figure out what X naught is by inverting this matrix and solving this integral. So this integral requires y tilde tau from 0 to t. So I have a history of observation. What do I do with that observation? Well, I construct this particular matrix. This is tau. This is a very big tau. Now I have a small tau. Yeah. So I do this matrix exponential. I do multiply it by C transpose. I multiply it by my updated observation. take the integral, multiply it by the inverse of the Gramian, I get the value of x naught. Okay. So I'm able to, so if O is full rank, I can reconstruct what my state was given the information after from time 0 to time capital T. What happens if capital T is very small? Okay, so let's say I pick capital T to be 10 raised to minus 10. Okay, so I look at a very small set of observations, and it seems to me that I'm able to reconstruct x naught, right? So almost real time, I'm able to reconstruct x naught. Is that a good idea or a bad idea? Yes, please.
I would think it would be a bad idea.
Why?
Because your data acquisition pipeline may not be accurate enough to give you.
Wonderful. Perfect. So the data pipeline, you might be actually accessing this observation data every 1 second. So you can't really do it. You can't do it with at the frequency of 10 raised to minus 10. Let's say you are making capital T. Let's say you have a very good data acquisition module. So you're able to take the data at that particular frequency, 10 raised to minus 10. I don't know. Let's assume that for the time being. Is that still a good idea? Why? Why do you think it's not a good idea?
If print T is too small, then you're very sensitive to any noise in your sensor.
Perfect. So you are very sensitive to noise. More importantly, this matrix will be very small. Remember, this is an integral from 0 to t, 0 to capital T. So this integral is going to be very small. So this matrix is going to be very small. I'm inverting a small matrix. What happens when you invert a small matrix? Any small errors that you might have made gets amplified. Okay. So if you're making any noisy measurement here, or if you're taking a noisy inverse of a matrix, then in that case, all of those errors will get amplified and you won't get a good idea of what x naught is. So naturally, you don't want capital T to be very small. You want to pick a reasonable value of T. But then in that case, you get x naught, you get accurate information about x naught after a certain point of time. So you're not getting that information in near real time. If getting near real time information is very crucial, what would you do? If you really need to know x naught or whatever, xt at every point of time, what are you going to do?
Filter, like a smooth out function.
Filter, okay, filtering will still require a lot of observations. You still need to do all this stuff with filtering. Any other idea?
You can write a state estimator.
State estimator is pretty much similar to filtering. So yeah, you will need a lot of observations in order to be able to filter and get the value of state. Any other idea? Don't cheap out on sensors. Okay, put more sensors. So you will have to put one sensor per state in order to be able to measure the state, in which case the C will become an identity matrix or something which is an invertible matrix, right? So that's how you're able to get accurate measurement of the state in sort of real time. To give you an example, if you were driving a car without what is that sensor in the vehicle tires that measures whether your vehicle is slipping or not slipping? Whatever, it triggers ABS control in like winter conditions whenever there is like snow or ice on the road. And so you have one sensor each tire. It's not like you have a single sensor for the entire vehicle, because you need to know which of the tires are losing friction with respect to ground, so that you can appropriately send the different torque to different wheels, so that you don't slip and maybe get into an accident. So you have to put 4 sensors on each of, like one sensor on each of the wheel, for you to be able to control the vehicle in a reliable fashion. So those are the situations where you have to invest in sensors. You can't just have one sensor and expect it to work wonders. Okay. Lemma, proof of lemma 5.36. I'm going to do the same thing we did in the previous class. I'm going to first show that the null space of the observability matrix is a subset of the null space of observability Gramian. So X is in null space, implies CA raised to kx equals to 0 for all k. This implies that summation of k equals 0 to n minus 1 alpha k t that proves the result. By the way, this k is from 0 n minus 1. So if X is in null set, then X is also in the null space of W0, WO, and that implies that null set of observability matrix is a subset of null space of WO. Okay, let's look at the other way. How do I prove this result? So it means that summation, okay. So this is step 1, this is step 2. Let X is in null space of W0, 0t. This implies summation of alpha kt c a raised to kx equals to 0, k equals 0 to n minus 1. This is 0 for all t greater than 0. These are linearly independent time signals. When can linearly independent time signals multiplied by something is equal to 0? When these coefficients themselves are equal to 0. Hence proved. This is a very typical way of establishing the result. If two sets are equal, you show one set is a subset of the other set, and then you show the other set is a subset of the original set. And this is how you go about proving it. Any questions so far? What we have proved is the null space of O is the same as null space of WO. Now the next result is that the unobservable subspace, so the set of X that you cannot observe by looking at the output, is the same as the null space of the observability matrix. I am missing ULL. Okay. Let's look at the proof of theorem 5.37. Okay, I'm going to do the same thing again. I'm going to assume that X is in RO bar, our unobservable subspace, and I'm going to show that X is in the null space. So X is in I'm going to take the differentiation. There are many ways to prove the result. We can, of course, use the result that we just proved about this case as well. But, I think I wrote the proof of this result in the previous proof. Nobody corrected me. Okay, so I needed to prove that the null space of this is the same as null space of this. I think that proof is wrong. The proof that I just said was the proof of this particular result. But anyways, there's another way to prove this result. Let me do this particular proof, and then I'll go back to the proof of null space of this is a subset of null space of O. The previous second part of the proof is wrong. So I'm going to take the kth derivative and I know that this is going to be equal to 0. I'm going to evaluate it at t equals to 0. And it turns out that this is, because the signal as a function of time is identically 0, if I take the kth derivative, that's also going to be 0. And this is okay. Right, so if X is an unobservable subspace, then X is also in the null space of the observability matrix. Let's look at the other way around. Right, this one is So this one implies that C a raised to kx equals to 0 for all k, and this implies that C e raised to atx, which is summation okay. Any questions on this one? Okay, so this one is this one proves that the unobservable subspace is equal to the null space of the observability matrix. Null space of observability matrix is equal to the null space of observability Gramian. Now there is one part in the previous proof, the step 2 of the previous proof that is missing. So I'll just write that down. You can maybe edit your proof accordingly. Any questions on this before I raise? No? Okay, so in 5.36 step 2, here is the step missing. X is in null space of W0, 0T implies X transpose well, actually it just means this, which further implies so this is the argument that was missing in the previous proof. So you can just go back and add that comment there. Okay. So what we have done so far, given a linear system, I can construct the observability matrix. It's a matter of a few matrix multiplications. Very easy on MATLAB, very easy on microprocessors to be able to compute the observability matrix. Finding the null space of observability matrix might require some effort because it's non-trivial to figure out what the null space of a matrix looks like. But as soon as you know what the null space of the matrix looks like, you essentially have characterized the unobservable subspace of that particular system. If you're happy with the unobservable subspace, you don't have to do anything. If you're unhappy with that unobservable subspace, that you're not able to distinguish between x1 and x2, then you have to put more sensors on that system, you have to expand the matrix C, and only then you will be able to be happy. So in today's world, let's go back to 20 years ago. You have a battery pack, you put one temperature sensor, and that was the temperature sensor that is supposed to give you the information about the temperature of the entire battery pack in the car. It led to a lot of uh, uh, thermal runaway in the battery. So you wanted to get a better understanding of what the temperature of the each cell in the battery looks like, because you could have a situation where one cell is extra hot and other cells are not. So you wanted to get temperature information of each of the cells in the battery. You expanded, you added more temperature sensors across the battery pack, and then you reduce the unobservable subspace of your battery pack. Even now, even today, you don't have a temperature sensor inside each cell. Okay, you only have temperature sensors over the battery pack. So there is still unobservable subspace within the battery pack. You don't know if this cell is hot or this cell is hot, but you kind of have an idea of which area of the battery pack is hot. Okay, so you still have non-trivial unobservable subspace, but you are happy because the batteries are not uh, going through a thermal runaway event. uh, what is the other situation? Even for the voltage, like, state of health of batteries is a very important topic in automotive systems. I'm sure many of you might be working on it with your advisors on this topic. Even there, the problem is that you cannot have a voltage and current measurement for each cell in the battery pack, and you may have 8,000, 10,000 cells within a battery pack for a vehicle. So you can't put 10,000 voltage sensors and 10,000 current sensors. If you can put it, if you have that kind of money, that's great. Then you have the information about each battery pack separately, and that's an important that can give you important information about which cell has gone bad, and maybe you can swap bad cells with good cells and be able to maintain that battery for longer. But right now we don't have that much money to put like 10,000 voltage and current measurement for each cell within the battery pack. So you still measure it in aggregate, and you have non-trivial unobservable subspace, and so you could have a few bad cells within your battery pack and you still cannot detect it because it's in the unobservable subspace of your system. Okay, so so we have characterized this. Now we need to figure out under what conditions can I, like, what is the way to figure out what x naught is given the information, given the observation that I've made so far. So this one is actually extremely simple and straightforward. Uh, let's do it. Why not? We have time. So I have y tilde t equals to c e raised to at x naught. So I have w0 0 t inverse integral 0 to capital T e raised to a transpose tau c transpose c e raised to a tau x naught d tau. This is a constant, so I can move it out. And I get w0 x naught. This one is an invertible matrix, so I get x naught. Okay, so I can come up with the information about x naught by looking at the observations from time 0 to time capital T. Any questions so far on these three results? No? Let's go back to the storm drain example that we started with at the beginning of this class and try to figure out what exactly is the unobservable subspace there. And knowing well that that particular problem appears, I mean, it's just a stylized problem, but that problem appears in battery pack, that problem appears in a lot of other situations. So let's see what happens. So I have x dot t equals to minus lambda 0 minus lambda xt and yt xt. So this is my C matrix, this is my A matrix. So the outflow from each pipe, from each drain is going to be proportional to the height. So remember x1 and x2 was the height of that drainage system. So the outflow is proportional to the height, and the measurement, the total measurement, which is the outflow from the main storm drain that is draining into the river, that's equal to the sum of the outflow from each of the pipes. Okay, there are some constants and proportional constants, but I'm kind of averaging it all to one. So the actual equation might look slightly different, but they all differ only by a constant. So what is my observability matrix here? That is C and CA. So C is simple, it's 1, 1. What is CA?
Negative lambda, negative lambda.
Yeah. What is the unobservable subspace? What is the null space of this particular matrix? So the null space alpha is already taken. How about 1 and minus 1? No, not minus, 1 over lambda. Does that look correct? No, 1 minus 1. Does that look correct? Yeah, that looks correct. Okay. What does it mean for this null space to be 1 minus 1? What that means is I cannot differentiate if I have x naught or x naught plus 1 minus 1. I cannot differentiate between these two starting conditions. So going back to the pipe example, I want to draw that. Let me draw here. So I have, this is my x1, this is my x2. Yeah. I cannot differentiate between this starting condition and this starting condition. Okay. So this one would be like, this is x1 plus 1. Sorry, this is x2 plus 1. This is x1 minus 1. There is no way for me to differentiate. You can give me the entire time series from the beginning of the universe to now, and I will not be able to figure out whether we are in this situation or whether we are in this situation. What happens in this situation? There is flooding. Okay, so this situation corresponds to the flooding event where the water is not able to go through the pipe. So this leads to flooding event in some part of the town. And just by putting a sensor here, you won't be able to figure out if there is a flooding happening in certain part of the city or certain part of the campus or not. So you will have to put, so if flooding is your main challenge, if you care about flooding, if you care about stopping flooding, then just putting one sensor here is not enough. You need to pay money to put a sensor here and put a sensor here, and then you can detect flooding as soon as it happens. Does that make sense? Okay. Any questions or concerns? Yes, please.
I guess I was curious, this is not so much like the math, but like in terms of the development of some of these models, do they usually start with more measurements, like in the prototypes of products, and then decrease like the observability, or do they start with less and increase? So,
you know, that's a great question, and the way I'm going to answer it is slightly convoluted. So at the very beginning, at time t equals to 0, you start with a lot of sensors. You will put camera, lidar, this and that, and you know that happens in university setting, right? That's what we do in our lab. We have like 500 sensors trying to figure things out. What generally tends to happen is you use all that data to model the system. You want to come up with the A, B, and C matrices with very high confidence that this is what the A, B, C matrix looks like for this particular system, and you use all these different sensors to figure that out. Once you have figured out the A, B, C matrices, then you put just the enough sensors that the customers are willing to pay for. Okay. So the willingness to pay of the customer who's going to be the end user of that particular product, that drives the decision about, and the safety and the law and the rules and the regulations, all of that combined determines how many sensors you want to put on that system. So to give you an example, you know, let's say my music system in my vehicle. It's a very old vehicle. The music system is old. Do I really care whether the amplifier is able to give me whatever the promised amplification was at the time the vehicle was manufactured? Probably it doesn't matter to me. I'm happy with whatever music is coming out of my music system. And therefore, there is no sensor to measure it inside the vehicle that, oh, you know, look, your amplifier is no longer working because, you know, we promised this much performance, but right now the performance is pretty poor. On the other hand, if you look at my tire sensors, for instance, the pressure sensors, the tire monitoring, the slipping monitoring and all that, whatever it's called, those sensors are all working, and those are supposed to be there because those are safety hazards. And I want to make sure that my vehicle is safe, even if I happen to drive on a highway and I encountered black ice somewhere on the highway. So that's both maybe a legal requirement. I don't know whether it's a legal requirement or not, but it could be a legal requirement. It could also be a requirement from the vehicle company itself. Like some engineer in the vehicle company said, we don't want people to die just because they happen to slip on the ice. And therefore, we'll put these sensors, even though it costs us $10 extra. And we'll ask the customers, hopefully the customers, when we tell them that, look, this vehicle costs $20 more because we have put all these sensors on it, maybe the customers will understand and be willing to pay $20 more for this vehicle. So sometimes, you know, there's a lot of considerations that happens about which sensors to put on the vehicle. Most of that is part science, but part willingness to pay from the customers. Sometimes, you know, you can put more sensors than what is needed, purely to get redundancy. So for instance, in the flight, in airplanes, you have these pitot tubes all over the flight, like not just at two places. All you need is the velocity of flight with respect to the air. So one pitot tube is good enough. You don't need like 10 pitot tubes to know that, but you still put 10 pitot tubes all over the plane because you want to have redundancy in that sensing. So there's a lot of stuff that happens behind the scene to figure out how many sensors and what sort of observability matrix we want this particular system to have. Any other question? Okay. Let's go back to our discussion on constructibility. So going back to this water example and building upon that previous question, the city must be having flooding for a long time and people didn't care about it. They are like, whatever, it's okay, it's part of life. And then someday some citizen stood up and said to the government, look, we have this flooding going on, my sofa got destroyed in this flood, I want you guys to do something about it, right? And so that became, it's not really a legal requirement, but if citizen is telling you to do something, you have to do something about it. So then you start putting sensors all over the place and get the whole system up to date. Okay. So definition 5.40, we have X unconstructible ut is identically 0 for all t less than equal to 0 implies that c e raised to at x is equal to 0 for all t less than equal to 0. Now I want you to keep in mind that this is for all t less than equal to 0. So the unobservable was t greater than equal to 0. Unconstructible is t less than equal to 0. What is this? Cn bar. Okay, that's just the definition. Unconstructible, if you give me the entire history of observations, I still cannot reconstruct the state for all time t less than equal to 0. So this is the observation for time t less than equal to 0. I still cannot figure out what my state is given that you have given me all the information about the past observations. The unconstructible subspace is given by this expression RCN bar. So Cn stands for constructible, bar stands for unconstructible. This is the unconstructible subspace. And AC is completely state reconstructible if and only if the unconstructible subspace contains only the zero vector. And as was the case for the reachability versus controllability, right? So the uncontrollable subspace was the same as unreachable subspace. The same thing happens here as well. So we have theorem 5.41, which says that R Cn bar equals to R O bar. So unobservable subspace is the same as unconstructible subspace. And the proof is the same argument that we have done before, so I'm not going to you can sort of modify the arguments that we made in the previous proofs to prove this particular statement. RCN bar equals to RO bar. And that concludes our discussion on observability. Okay, we talked about two, so and that also concludes chapter 5. By the way, we are going to move on to chapter 6 after the break. So the things that we have learned so far is controllability, reachability, observability, and constructibility. Those are the 4 concepts we studied in chapter 5. The idea of reachability is going from state 0 to some other state. The idea of controllability is going from some other state to 0 state within a finite amount of time. The idea of observability is if you give me the future observation and action, I should be able to reconstruct what the past state was. And something that uses this idea is labor market. So the unemployment numbers, they keep getting updated over time. I don't know if you have seen it, but the Fed chair looks at the unemployment rate in order to figure out what the interest rate should be. So that's the control system. And the unemployment today, so they have some information about what the unemployment rate of March is going to be, but by June, July, they will update the unemployment rate for March. Okay, so right now they are updating the unemployment rate for December. So December, they had some observation. January, they had some more observation. February, they had more observation. That led to update of the unemployment rate in December, right? So that's roughly what observability would mean. And constructibility means that I have all the past history of observations and action. I want to figure out what the current state is going to be. And that's constructibility. Turns out that unobservable subspace is the same as unconstructible subspace. So if your state is in the unconstructible subspace, you will not be able to reconstruct that particular state given the observations from the past. So this gives you the fundamental limitations of a system, right? And how do you overcome the fundamental limitations? How do you overcome the uncontrollability? You add more control, more actuators to the system. So then the system becomes controllable, the system becomes reachable. And I gave you the example of airplanes. So what Wright brothers did was not to put wings on a structure and make it fly. That many people did that before it. They actually added a vertical tail and a horizontal tail, and that's what made the planes fly in a controlled fashion. So they made stuff reachable by adding more control surfaces to the flight. Observability, on the other hand, is about being able to figure out what the state of the system is given the observations, given the output. And so in order to improve observability of the system, you have to add more sensors, you have to spend money. I mean, both for reachability and controllability, you have to pay money because you need to add more actuators. So instead of having just one brake in the vehicle, you have 4 brakes in the vehicle to stop the vehicle in the event of imminent accident. So you have to spend more money on the vehicle to make it controllable. And the same thing happens with observability. You have to put more sensors. So another way to think about it is drug companies are trying to make our body controllable because they are inventing new drugs that changes the health state of our body. So X is the health of our body. And the diagnostic companies, the medical diagnostics companies, they are the ones who are making our bodies observable. They create X-ray machines, they create CT scans, MRI machines, and so on, which helps us figure out what's happening inside our body and therefore make our body observable, make the health condition of our body observable. There are still many situations where it's not observable, like the kind of problems that we have in our body is not observable using the current diagnostic tools, and therefore the companies are investing money and doing research to make things more observable. Okay, so that's all I wanted to discuss. We have understood the fundamental limitations. In the next subsequent lectures, we are going to talk about Kalman canonical form, which tries to come up with a different state representation. So right now what we have is a natural state representation. So X is something that we naturally think of: height, length, breadth, temperature, and so on. How can you transform the state to through similarity transform? Can you change the state equation and the observation equation and so on in order to represent it in a format that's much easier to understand and interpret by hand? So that's something that we'll talk about, Kalman canonical forms, in the next class. And then the subsequent classes will talk about observer design and then control system design. So observer design is to be able to figure out what the state is given the observation, and the controller design is to figure out how should you control, what should the control policy look like that helps you achieve the goal for the system, which in some cases is going to be stability, but in other cases it could be even optimizing some metric, some cost function. So we'll see how much we can get done by the end of the semester, but that's roughly, like, today is the midpoint of the semester, and so we'll see how much we are able to cover by the end of the semester. So thank you so much, and I'll see you guys after the break. Have a great break.